So find all values where you have a horizontal tangent. Thank you. Okay. So horizontal tangent, what does derivative give you in one word? Slope. And when a line is horizontal, that means the slope is what? 0. 0, right? So what we're looking for is where the derivative equals 0. You solve, you get plus or minus root 2. Now, a couple little things come out of this. Number one, whenever you are doing a free response question on the AP exam, if you ever have to solve an equation, you have to write the equation you're solving or you won't get credit for the solution. So if I'm finding the zeros of this, I have to write that I have set this equal to 0 or I don't get credit for my answers. They don't care how you solve. Like, you don't have to have any steps in between as long as you have the equation written and then your solutions. So you can write as many or as few steps in between as you want, but you have to have the equation written and your solutions. Okay. This would not have any vertical tangent lines, but a vertical line has what kind of slope? Undefined. Why is it undefined? Because it's vertical? You just said a vertical line has a slope that's undefined, and it's undefined because it's vertical. Yeah. Okay. All right. So there's two main reasons, right? So we all know slope. When you're on a vertical line, there's only one x value, right? All the x values are the same, right? You'd have the line x equals 3, right? So since there's no change in x, you have division by 0 in your slope formula. And so you end up with that undefined slope. The other reason is numerically, if you have a line that's horizontal, so the slope is 0, as the line gets steeper, the slopes get bigger, right? So you end up with a slope of 1, and you keep going, slope of 2, slope of 10, slope of 50, slope of 100. What are the slopes approaching? Infinity, right? So like up 10,000 over 1, up 100,000 over 1. And you just keep getting steeper and steeper, but there's no like final number. It's infinity. So because of that, infinity is an undefined term, so therefore the slope is undefined. Yes, Al?
So could you technically have like a vertical line of like negative infinity as your answer?
Like for a slope?
Yeah.
So could you have a slope that is negative infinity or infinity?
For like one of these vertical tangent.
Oh, vertical tangent. Okay. So what would happen is if you have a function that ends up with some sort like here, where you have a vertical tangent like that, the function itself, when you take the derivative, your f prime will have some, like say this is at 2, then you would have division by 0 at that x value, and you'll end up, when you do the derivative analytically, you'll get a does not exist on your derivative. So you just say undefined. And so if they ask you where does the tangent line go vertical, it's all the spots where the derivative is undefined. So whatever makes you divide by 0. Right? Okay. There's actually another way another thing that division by 0 can cause, but we'll get into that later. Division by 0 might not cause a vertical tangent. It might cause what's called a sharp turn, but that's for another day. All right. Today we're doing 3-7, applications. Today is a big, heavy lesson, but we're not going to get to all of it because I wasted 10 minutes of your time telling you personal stories. So that's all right. We'll get to most of it. Yes?
How would you shorten that so we can put it as an
3.7 applications. Today's applications of the derivative. On Monday, it's also applications, but it's a different type. So today we're doing just generic instantaneous rates of change, but with words. On Monday, all of our rates of change will be with respect to time, and they'll be with respect to other rates. So Monday, we have a lot of implicit differentiation to do. Today, we don't have any. And then Tuesday is our last lesson of the unit. So Tuesday is linear approximation. It's fun, it's easy. So we do that lesson on Tuesday, and then Wednesday we start reviewing for your tests, right? So Wednesday we review, next Thursday is your big quiz, then you get Friday off, you get a nice 3-day weekend, and then the following Monday we review again, and then we test on Tuesday. So, yes.
Friday before, like the Friday the week before MEL?
Yeah, a week from today you have off. It's Professional Development Day for teachers. We don't have it off, but you guys get it off. Yay. All right. Okay. Okay, you don't write this down. All right, this is just a lot of words to tell you to review a concept that you already know. So what I'm starting you off with here is making sure you understand that delta y, delta x, or change in y over change in x, that's your slope of the secant, which gives you an average rate of change, right? So if I want an average rate of change of something over an interval, then I use this formula. As soon as I take the limit as this change in x approaches 0, as the x values approach each other, then I end up getting an instantaneous rate of change at a specific spot, and that's called the derivative, right? So the derivative is really the limit as delta x approaches 0 of the slope formula. So this, like, without the limit, you have average rate of change. With the limit, you get instantaneous rate of change. Okay. Today we'll be using this in a variety of applications. Now the first application is motion. We're going to spend a long time on motion. So I call motion PVA. What does P stand for? What about V? What about A? Acceleration. Yes. So all of our motion in Calc AB is linear. It's all motion in a line. We're either moving horizontally or we're moving vertically. When you get to BC, you get to do motion in 2 dimensions. So in order to do motion in 2 dimensions, you need to use vectors. So you have to wait until Calc BC to do vectors. It's not heavy vectors. Did you guys do vectors last year? A little bit? Okay, you'll be fine. So anyway, but for today, we're just doing linear motion. So I have on the board the top 10 things you need to know about linear motion, but we're afraid to ask. Okay, so the first one you should already know, but we'll write it anyway. Velocity is the derivative of position. If you're ever asked for the velocity function, you just differentiate your position function and you get velocity. And I'm going to write this as V equals S prime of t, if S is your position function. All right, acceleration is the, second derivative of position or first derivative of velocity, right? Okay, so acceleration is the derivative of velocity. So I'll write both of those. So we have A of t equals V prime of t, which equals S double prime of t. So acceleration is the rate of change of the velocity. Distance is the total amount you've traveled. We haven't done a lot of distance versus displacement. Distance is, like, if I walk 10 feet this way, and then I turn around and I walk 10 feet back, my distance traveled would be 20 feet, right? It's how far I had to walk. But my displacement is how far I am from where I started. So my displacement would just be 0 because I didn't actually change position from beginning to end. Average velocity is computed as displacement over time. It's your ending position minus starting position over ending time minus starting time. So displacement over time. You would think average velocity would be distance over time, but it's actually displacement over time. A particle is at rest when the velocity is 0. This is important. This gets asked a lot. When is the particle at rest? How do you know? You set your velocity equal to 0. All right, the next one. Oops. A particle is velocity. Velocity has two important things about it. So most people will say velocity is a vector. It has a magnitude and it has a direction. We're not going to treat since we're just doing linear motion, we're not going to write velocity as a vector. Velocity is just going to be a number, but the absolute, like the size of that number, the magnitude of that number is how fast you're going. The sign, S-I-G-N, the positive or the negative with it, tells you what direction you're going in. So the College Board, I know in physics, like you can go down and have a positive velocity if you're talking about like in relation to something above you kind of a thing, like it's all in relation to other stuff. The College Board doesn't get that complicated. The College Board pretty much says if you're moving up or to the right, you have a positive velocity. If you're moving down or left, you have a negative velocity. And that's as deep as they get. So you don't have to worry too much in the College Board about like in relation to stuff. You just up, right, positive, down, left, negative. This book, they talk forward and backward. So again, forward means positive, backward means negative. So, okay. All right. Velocity is increasing when the acceleration is positive. Why? Because acceleration is the slope of the velocity. When you have a positive slope, you're going up. When you have a negative slope, you're going down. So velocity is increasing when acceleration is positive, decreasing when acceleration is negative. The biggest mistake that students make is confusing velocity with speed, which is what we're about to define. Just because your velocity is decreasing doesn't mean you're slowing down. And that's where students have a hard time. Velocity can be decreasing and you're actually speeding up. So I'll show you this numerically once we get through all 10 of these. Same thing vice versa. Velocity can be increasing and you're slowing down. All based on the sign. Okay. Number 9. Speed is the absolute value of velocity. Now in this unit, that's good enough. Speed is the absolute value of velocity. Later on, when you get into vectors, then you can say speed is the magnitude of the velocity, because that's really what it is. By those absolute value signs, we should never say absolute value. We should always say magnitude, because that's really what an absolute value gives you. It gives you the magnitude of whatever's inside. So speed is the magnitude of the velocity. And the last thing is probably the most important, which is, and this is on, I guarantee the College Board's going to ask this on the AP exam. Speed is increasing when velocity and acceleration have the same sign. Speed is decreasing when velocity and acceleration have opposite signs. All right? Speed it's not just based on acceleration. You have to know both. So when velocity and acceleration have the same sign, your speed is increasing. Even if they're both negative, your speed is increasing. Suppose these are velocity values. So here's the thing. So if my velocities are positive and they're increasing, that means that I'm going, like my velocities are moving in this direction. So my velocity, when my velocity is positive and my velocity is increasing, then my speed is increasing. So like if I'm in a positive area and I'm increasing, so velocity is positive and acceleration is positive, then my speed is increasing. Say I'm down here. If my velocity is negative and my acceleration is negative, so that way, then what's happening with my velocities? So they're technically decreasing. I'm going from -1 to -2 to -3 to -4 to -5. The numbers are decreasing numerically, but the speeds are the absolute values of those numbers. And the speeds are getting bigger, right? 1, 2, 3, 4, 5. So even though numerically your velocities are getting smaller, your speeds are getting bigger, right? So you gotta be careful not to get those mixed up. So velocity increasing and decreasing just has to do with acceleration, positive or negative, but it doesn't tell you if you're speeding up or slowing down. So to know if I'm literally driving faster, I need to know if my speed is increasing, and then I got to know if both the velocity and the acceleration have the same sign at that point. Then you'd just be 0, right? You wouldn't be speeding up or slowing down because your velocity would, or your acceleration would just be 0. Yeah. Okay. Now the next 15 minutes, we have a wonderful PVA problem with K parts. So I've spread it over 3 screens. Are you ready?
Already.
You are so ready. All right. I'm going to change. I don't want to call this F of t. I just want to call it S of t. So just call this position function S of t. So S of t equals t cubed minus 6t squared plus 9t. That's going to be our position function. Time is in seconds. Position is in meters. Write what I want you to do. Don't write all 4 questions and like bam, 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 bam. Write a question and its answer, and the next question and then its answer, question and answer, so that you can see what to do for each thing, right? So we're going to do part A first. Find the velocity at time t. Well, okay, would this be an average velocity or an instantaneous velocity? It's an instantaneous because they say at time t. Now, the other key is if they want an average velocity, they'll say they want an average velocity. You'll see the word average in the question, right? They'll never ask for an average velocity where they don't say the word average in the question. But instantaneous, they'll just say velocity. So if they just say velocity, they mean instantaneous velocity. All right, so how do I find velocity? Velocity is the what of the what? Derivative of the position, right? So v of t equals s prime of t. So what's the derivative of this function? Just yell it out. Plus 9. Any questions on that one? Good. Part A is done. Part B. What is the velocity at 2 seconds and 4 seconds? So we're just looking for v of 2 and v of 4. So no calculators, just see if you can plug these numbers into your velocity and find those velocities. 10 seconds or so. All right, so v of 2, so 3 times 4 is 12 minus 24 plus 9. Technically, could I leave it like that? Yeah. First, I think I would go ahead and figure out that it's -3. All right, so -3, what would the units be? Meters per second. It's the units of position over the units of time. This would be in meters per second. v of 4, so 3 times 16. So 48 minus 48 plus 9. So I get 9 meters per second. Any questions on that? Just plug in the numbers. Not so bad. Okay. Let's do red. So, part C. How do I know when something's at rest? Velocity is 0. So you're going to set your velocity equal to 0 and solve. Take a minute and solve that equation. And I would divide the 3 out before doing anything else. Now, suppose I asked you this question and I added these 3 beautiful letters. Justify your answer. All right, so when you have to justify your answer, it means I want to see the word because in there somewhere. I'm looking for a because statement. So here's what I would say. I would say the particle is at rest at t equals 1 and 3 seconds. Make sure you always put units in your answer. T equals 1 and 3 seconds because, how did we know? V of 1 and V equals V of 3 equals 0. Because the velocity was 0 at those times. All right, last part on this screen. Which is, when is the particle moving forward? That is, when is it moving in a positive direction? Okay, so when is the particle moving forward or in a positive direction? All right, we know that something is moving forward when what is what? Velocity is positive. How do we know when your velocity is positive? It's our first time making what I call a velocity sign line. I call them sign lines. You might call them sign charts or sign graphs or number lines. You will always hear me call them sign line just because it rhymes. So, all right, so we're going to make a velocity sign line. Now, before we do this, there was a stipulation to this problem that did not get printed, which I'm going to add in right now. So I wish they'd said this, but they haven't. So we should mention that t has to be greater than or equal to 0. We're only going to deal with positive times. We're not going to deal with negative times. Okay. All right. So we need to know when this particle is moving to the right, so we need to know when velocity is positive. We have to make a sign line. Now, I'm going to write something I'm going to erase, so don't copy it, okay? So if I make a sign line, typically when I start a sign line, I make a number line that points into infinity in both directions. For this one, though, I'm going to cut it off because we don't want any negative times. So I'm going to start it at 0. Okay, so these are my times. These are going to be my velocities. The numbers you put on your number line are what we call the critical values for that function. Critical values are the input values that cause that function to be either 0 or undefined. In this case, we're talking about our velocity. Our velocity is never undefined, but it's 0 at 1 and 3. those are the numbers you want to put on your sign line. So these are called, some people call them critical values, some people call them critical points, critical numbers, right? Whatever you want to call them, just the word critical should be in there somewhere. So those are your places. Those are the values of t where interesting stuff happens. Really, it's the values that you have to be at rest in order to change direction. So it's the values of t that cause your velocity to be 0 on the time. All right, so now we are going to determine the signs of the velocity. By sign, I mean S-I-G-N, positive or negative, the signs of the velocity. So, Kirthana, how are you? Good. Pick a number between 0 and 1. Okay, Kirthana wants to pick a half. So we're going to go with a half. Now, we need to find out if the velocity is positive or negative at a half. Do not plug a half into this function, this polynomial, because that's kind of a pain in the butt, right? And I don't care. I don't want the number. I just want to know if it's positive or negative. It's much easier to plug into your factored form. So if you have factored your velocity, plug whatever number is in this interval into your factors, and you'll have a much easier time. So, Kirthana, are you ready? Yeah. Okay, so we're doing a half. Is a half minus 3 positive or negative? Negative. What about a half minus 1? Also negative. What's a negative times a negative? It's a positive. So we are going to put a little plus right there. You have done this. I know you have. Yes. It's probably been a while, but yes, you have done this before. So Zuhair, how are you? Okay, since you've done it before, right? This is like old hat. So pick a number between 1 and 3. 2. 2 minus 3 is negative. 2 minus 1 is, what's a negative times a positive? A negative. Mihika, how are you? Pick a number bigger than 3. 4. 4 minus 3? 4 minus 1? What's a positive times a positive? It's a positive. All right, so what that means, if we were talking about right, left, right kind of stuff, this would be to the right, this would be to the left, this would be to the right. In this problem, we're talking about forward, backward, forward. If it was a vertical, it'd be up, down, up, right? But anyway, positive velocity means we're going up or to the right or forward. Negative velocity means we're going down or to the left or backward. Okay, so the question asks, when are we moving forward? So we have to write this in interval notation. So the particle is moving forward on. You always say on an interval. All right, I'm going to write the numbers, and then I'm going to talk to you for a minute about like what we have to do with these. So 0 to 1, and then what's the other interval? 3 to infinity. And I'm going to put because our velocity is greater than 0 or positive on those intervals. All right. The College Board decided long ago not to care because there's a big controversy, and we'll get more into it in the next unit too, about whether or not you should include the 0, the 1, and the 3. Now, you can never include infinity, right? Like, nobody's going to argue that this should be a parenthesis. But should we include the 0, the 1, or the 3? The 0, you could make a pretty decent argument for it that, yeah, we are moving forward at 0. But some people would say, look, that was our initial spot. You're not, like, you're just starting. You don't even have really an orientation yet. So the college, and at 1 and 3, technically you're at rest, right? How can you be moving forward when you're at rest, right? Okay, so at 1 and 3, you're not moving forward, you're not moving back, you're not moving at all. So do we include them or do we not include them? The College Board decided long ago that they don't care. So you can get these wrong if you include something that shouldn't be included, but you'll never get them wrong if you just exclude everything. So whenever you're writing these intervals, always put them as open intervals. Always write them as open intervals. Hey, what's that like U thing that I put in the middle? I don't know what that stands for. Yeah, the actual word. It stands for union. Very good, Brian. Yeah, this stands for union. So what I'm saying is it's the union of these two sets. It's set notation for union. So the union of these two sets means include all of these values of t and include all of these values of t. Okay. All right. Are we ready to move forward? Good. That was parts A through D. Let's do parts E, F, and G. Now, when you have to sketch on a number line, the College Board is never, ever, ever going to ask you to sketch motion on a number line, ever. But your book, I think, asks you for it. So I'm not going to spend a lot of time on this. I'm just going to give you a little demo. So if we want the motion on the number line, and again, it didn't say if you want the number line to represent time or to represent position, but I'm going to have it represent position. So this is going to be our position. All right. So what you want to do is you want to find the position at all the interesting values. The interesting values would be what position were you at when you started, and then what position were you at each time you changed direction. We're going to find those 3 position values, and then we're going to sketch based on those. So what was our position at time 0? 0. All right, so we're starting at the origin. All right, at time 1, you just plug in a 1. You get 1 minus 6 is negative 5 plus 9 is 4. Plug in a 3, you get, I'm going to write it out, 27 minus 54 plus 27, so we're back at 0. All right, and I'm just going to, you don't have to redraw this, because I'm going to do it because it's on the previous slide. So just a reminder. All right, that was our velocity sign line, plus, minus, plus. So here's what happens. So we have, so we're going to have a position of 0 and a position of 4. Those are the only 2 positions that are interesting. So our first leg of our trip, we start at 0 and we travel this way. We go to the right up to 4. Then the next leg of our trip, we start at 4 and we travel back to 0. But after we get back to 0 again, we keep going. Now we're going to the right again, right? So after time 3, we start at 0, but now we just head to the right and keep going forever. Is that okay? Okay, that's as wacky as you need to make it. So I start here, I travel to the right until I get to my position, at 1, and then I stop because I've turned around. Now I travel to the left until I get to my next stopping position, which is at 0. Then I turn around and I head to the right for the whole rest of the time. Okay, that's all we're going to do with that. Okay, part F. Distance traveled is really easy with integrals. You guys don't know integrals yet. So you have to find distance the long way. So how do you find distance traveled? It's what? Okay, so we want the distance traveled from 0 to 4. So I'm going to add one more position value here. S of 4. I want to know where I'm at when I stop. So if we find S of 4 is 64 minus, 6 times 16, 96, plus 36. So negative 60 plus 64, I'm back at 4. So to find my total distance, so what you do, you list your starting, the position at all of the times you stopped, so like all your critical values, and then your ending. So you find the positions and do them in numerical order, times 0, time 1, time 3, time 4. So my total distance traveled. How far did I travel from time 0 to time 1? 4 meters, right? From time 1 to time 3, how far did I travel? Another 4 meters. Does it matter that it was in the other direction? No, not for distance. We don't care. From time 3 to time 4, how far did I travel? Another 4 meters. So my total distance is 12 meters. So really what you're doing is you're just finding the distance traveled for each interval of time. You can do it by 4 minus 0, 0 minus 4, 4 minus 0, but keep them all positive and just add them together. Displacement. Again, much easier to do with integrals, but that's okay. Displacement is just your ending position minus your starting position. So what's our displacement? 4. You can write 4 meters if you want. You don't have to say 4 meters to the right of where we started. That's okay. You just put 4. We have finished parts E, F, and G. Let's do parts H, I, J, and K. And then we'll be done with motion. Not done with applications, but we'll be done with motion. No, there's more. Okay. Was this an actual problem on your test? So your test will have motion on it. It probably won't be 12 parts, right? So I will tell you what the College Board does for if you take the AB exam where it's linear motion, then what they would do is they would give you a problem similar to this and pick 3 or 4 of these at random, and that's what you would answer, right? Same kind of thing on your test. We're not going to ask you 14 questions. We'll ask you probably 3 of them. So, but you just got to be ready for whatever we ask. Okay. These are easy though. What's the acceleration at time t? Oh, I'm going to rewrite the velocity. First of all, I'm going to recall this s of t. Oh, hang on. Go back. So this is called s of t. Oh my gosh, stop it. Okay. So v of t is for our 3t squared minus 12t plus 9. All right, so a of t. A of t is the what of the what? Derivative of the velocity. A of t equals v prime of t. All right, just yell it out. What's v prime?
6
minus 12. Done. See, we're already on part I. All right, what's the acceleration at time 4? Let's do a of 4. It is 12. Good. So units, if position is in meters and time is in seconds, velocity is the rate of change, so it would be meters per second. Acceleration is the rate of change of velocity, so it's meters per second, right? Or I heard meters per second squared. Either of those, you can write m/s/s, or you can write m/s squared. What you can't write is meters squared per second, because that's a totally different thing. All right. J. On what intervals is the velocity increasing? Well, velocity is increasing when the acceleration is positive. So we need to make an acceleration sign line. So first we need to know when acceleration is 0. We need to find our critical numbers. What's the only critical number? 2. All right, so make a sign line for acceleration times 0 times 2. Tyler, how are you? Pick a number between 0 and 2. 1. Plug 1 into your acceleration. Do you get a positive or a negative? Negative. Tyler, I'm going to just stick with you. Pick a number bigger than 2. Plug it in. What do you get? Positive. Which means our acceleration is negative. Our acceleration is positive. So our velocity is decreasing and our velocity is increasing. We are asked, when is the velocity increasing? Let's write our answer with a sentence. So v of t is increasing on the interval. What would the interval be? 2 to infinity and beyond. All right. Is on 2 to infinity because how did we know the velocity was increasing there? A of t was positive on that interval. Last part, part K. On what intervals is the particle speeding up? So we want to know when the speed is increasing. How do I know when speed is increasing? Yeah, Casper. When the signs of what?
Velocity and acceleration.
When velocity and acceleration have the same sign. So one of the ways to do this is to kind of line the sign lines up. So you have your velocity sign line, which has a 0 and a 1 and a 3 and goes plus, minus, plus. And you have your acceleration sign line, which has a 0 and a 2 and goes minus, plus. And you kind of put them together. If you want to, you could make like a V/A sign line or kind of write the signs together. Here, I'm going to do it with red. Like put all the numbers, 1, 2, 3, and then say, all right, so we had a plus and a minus. And then here from 1 to 2, we had a minus and a minus. And from 2 to 3, we had a minus and a plus. And from 3 on, we had a plus and a plus, right, for our velocity and our acceleration. Just so you can kind of see it a little better. But you don't have to, just so you know, the College Board will never, ever, ever look at a sign line. They don't grade these at all. This is just for you to figure stuff out, right? So nobody cares about your sign lines. The sign lines are just a tool for you to use to figure out these problems. What they are looking for is the answer. So the particle is speeding up. I heard a question. What was the question?
On the past 3 on the VA, you have plus and minus.
Oh, whoops, sorry.
Oh.
Thank you. Good call. All right. So the particle is speeding up on what interval or intervals? Tell me the first interval. 1 to 2. Union with, what's the next interval? 3 to infinity. Because, how do I know the particle is speeding up then? You can't just say the signs are the same. You have to say velocity. There's no pronouns. You got to be very specific because V of t and A of t have the same sign on those intervals. You just did I parts of a linear motion problem. Well done. Okay. Whew. Look, we're only halfway done with notes.
Hour and a half long.
We're really not. It's a lot. The next ones are going to go real fast. Okay. 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 So don't write this down. Don't write it down. We're going to get into other applications now. You will have some other applications in your homework. There's going to be a lot of PVA, but there will also be a couple of other applications as well. So here's the thing. So this is just to kind of get you to appreciate calculus. Like this section is supposed to answer the question of like, when is this ever used? Here's how it's used, right? So this is why they put this section in. So we do a lot with density in Calc 3, not so much linear density, but density over surfaces. But anyway, if a rod or piece of wire is homogeneous, then its linear density is uniform. And the density is defined as mass divided by length. That's your density. And it's, in this case, kilograms per meter. Suppose, however, that the rod is not homogeneous. And its mass is measured from the left end to some point x. All right? So if we have some rod and the density changes throughout the rod, so then the linear density of the rod is defined as the rate of change of the mass with respect to its length. So linear density, this is our first application. You don't have to have these memorized. We will never say, what is the linear density without defining it for you. We'll always explain what it is. So the linear density is, which density, just so you know, it's almost always called rho, R-H-O, rho is the Greek letter. So rho, it's the limit of the rate, as your change in x approaches 0, of your mass divided by your length. So it's dm dx. X is your length, m is your mass. Mass divided by length gets you your linear density. All right. Okay. So you don't have to know this. Like, I want to stress this through all the rest of these applications. No one is ever going to test you to see if you know what marginal cost is or what linear density is. We'll always explain it to you. Okay, so let's do this in a problem. So, suppose the mass equals the square root of x, where x is measured in meters and m, the mass, is measured in kilograms. First, we're going to find the average density from 1 to 1.2. Then we're going to find the linear density at x equals 1. So really, we're doing an AROC and an IROC. So your average density, remember density is it's change in mass over change in length. So our linear, or our average density would be m of 1.2 minus m of 1 over 1.2 minus 1. In each group, I want one person to pull out a calculator and compute this. So elect a person in your group to crunch the numbers. How many decimals do you have to be correct to? Always minimum 3. Minimum 3. We don't, and do you know where it says that? In your syllabus that you all read. So, okay, always 3. And on the AP exam, same thing, always 3. It says it doesn't say it problem by problem, it says it one time in those paragraphs of directions at the beginning of the exam, right? So always 3 decimals. This one, you should get around 0. What? 477. You actually get 0.4772 if I remember right, going to 4 decimals. The reason I'm going to show you the 4th decimal is not because you have to write it, because I want to explain that when you say this wasn't a 2, let's just pretend for a second that it was an 8. If your fourth decimal is an 8, you can write your answer as 0.477 or 0.478. They accept the rounded or the truncated answer. They don't care. So as long as those 3 decimals are correct, rounded or truncated, they're fine. All right, units. What is mass measured in? Kilograms. What is length measured in? Meters. There's your units. It's the units of mass over the units of your length. All right, linear density. That's the derivative of the mass with respect to length. That's your instantaneous rate of change. Everyone take a second and find the instantaneous rate of change of m with respect to x. Anthony, how are you? I'm doing okay. All right, so really all I'm looking for is the derivative of x to the 1/2, right? You can tell it to me in any format you want. What's the derivative of x to the 1/2? Okay, that works. I personally would have written 1/2 x to the negative 1/2, right? And then you can simplify that. You like jump to the end, which is fantastic. 1/2 root x. Well done. If we want the density at x equals 1, you're just plugging in a 1, and you get 1/2. What would the units be? Still kilograms per meter. Does it make sense that our instantaneous rate of change at 1 is pretty close to the average rate of change from 1 to 1.2? Yeah, that's pretty close. And it should be, right? You haven't traveled very far. Okay. All right. That's your first application. Okay, don't write this down. Let's just talk about it. Population growth. So, when we have a population that's growing, the average rate of change or rate of growth of the population, that's your change in population over change in time, right? So if we want an instantaneous rate of growth, that's the derivative of population with respect to time. So here's our example for this one. Consider a population of bacteria in a homogeneous nutrient medium. Suppose that by sampling the population at certain intervals, it is determined that the population doubles every hour. If the initial population is n sub 0 and time is measured in hours, then if you double every hour, your function for your population at any given time is the initial population times 2 to the t. So if the initial population is 100, find the rate of growth after 4 hours. Round to the nearest whole number. So our f of t, if our initial population is 100, is 100 times 2 to the t. Let's see if you remember the derivative of 2 to the t. So I want you to see if you can differentiate that function. 2 to the t. 2 to the t. I'll give you a hint. It's not t times 2 to the t minus 1. Do you know the derivative of e to the t? What's the derivative of e to the t? E to the t, right? E is just a number, just like 2, right? The derivative of e to the t is e to the t. The derivative of 2 to the t is 2 to the t, but then you got to multiply it by something to convert it to a base e. So what do you have to multiply it by? ln2. So you have 100 times 2 to the t ln2. All right, so if I want the rate of growth at 4 hours, I'm looking for f prime of 4. So you could just tell me it's 100 times 2 to the 4th times ln2, and that would be exact. But I want to see if you guys can find this as a decimal. So hand your calculator to someone else in your group and let someone else crunch the number on this one. It only takes a second. There you go. By the way, notice that it said round to the nearest whole number. Make sure you pay attention if they tell you to round, that you round. Ian, what'd you get? 1109. All right, here's the question. Do you know the units? Bacteria per hour. There's always a per when you have a derivative. It's a rate, right? This is bacteria per hour. So what is that saying? That's saying that when t equals 4 hours, the bacteria, the population of bacteria is growing at a rate of 1,109 bacteria per hour. All right. Next. Don't worry, we're almost there. Okay, don't write this. You know what? I think I'm going to skip the chemistry. Do you want it? It's thermodynamics and compressibility. You had enough chemistry? But if you take chemistry, then you can relate to this.
I don't like
Skipping this is going to be your brain break. All right. Okay, let's talk cost. All right, so when you have a cost function, not in terms of time, but in terms of the number of products you produce, that's called your cost function for your company. So the cost function is the total cost that a company incurs in producing X units of some product, right? So if C is a cost function, if the number of items produced increase from X of 1 to X of 2, the additional cost, okay, average rate of change of the cost. So here's the thing. If you do the limit of the average rate of change of the cost, which means if you do the derivative of your cost function, the derivative of the cost function is called the marginal cost. You will hear this term when you take economics. You'll hear marginal cost. So marginal cost, and someday if you take economics in college, you can take calculus-based economics, right? And then you can do it with derivatives. In high school, you won't have any derivatives. But anyway, so marginal cost is the rate of change of your cost function with respect to the number of products you're producing. Now, this we do in Calc 3. We'll actually build these functions. It's kind of fun. It is often appropriate to represent total cost as a polynomial where A is your overhead. That's your rent, your heat, your maintenance. And then all the others are multipliers of your numbers of products based on material cost, labor cost, all these different costs associated with creating the product itself, right? So you build this polynomial based on different factors that go into how much it costs to create the product, and that becomes your overall cost function. All right, so that being said, so we are given a cost function of 10,000 plus 5x plus 0.01x squared. So the marginal cost which is dc dx, right, or c prime. Take a minute and find c C prime. Find the marginal cost function for this product. Emma, what'd you get?
5
Yeah, very good. 5 plus 0.02x. So if we want the marginal cost at the production level of 500 items, so we're looking for, just so you know, in math, if you have to plug a number in and it's not like a cute like f of x where you just stick something in the parenthesis to say f of 5. So if I have to plug a number into dc dx, the way that we write it in math is we write dc dx, a vertical bar means evaluated at, x equals 500, and you write like kind of low to the bottom what you're plugging in. So dc dx evaluated at x equals 500, so you're plugging in a 500 for your x, so it'd be 5 plus 0.02 times 500. Well, let's see, 0.02 times 100 is 2, 2 times 5 is 10, so we get 15. We need units. Dollars. That's it? It's $15 per item, right? Per product or per item. Yeah. $15 an item. What is that saying? That's saying that when we are producing 500 items, the cost of producing items is increasing at a rate of roughly $15 per item for each item we add to the production line. So, all right. All right, and so if we, I don't know how, we'd have to figure out how much it costs to produce 500 and then add 15 to estimate the cost of producing 500. All right. So, last one. Okay, we're done. We're done. Let me just read this to you. This is just your closing little slide here. So, calculus is used in lots of places. We use calculus in all of the sciences. A geologist is interested in knowing the rate at which an intruded body of molten rock cools by conduction of heat into the surrounding rocks. An engineer wants to know the rate at which water flows in or out of a reservoir. An urban geographer is interested in the rate of change of the population density in a city. A meteorologist is concerned with the rate of change of atmospheric pressure. A chemist wants to determine a reaction rate. Or an electrical engineer wants to determine the current through a copper wire. All of these can be done with calculus. Yay, calculus. Okay, so that is it for today. I'm going to kill the recording here.